Hello everyone, this is Maxime Flamand, CTO for 5G Automotive Association. Welcome to this online webinar. We are going to start shortly, waiting for people to arrive. I see quite many people joining in the lobby right now. So we are waiting a couple of minutes. Just as a note, we will share to all participants and people that have signed up for this webinar. We will share the presentation after. So be sure you're going to receive all the material. We are already about at 40 participants, so I think that it's the right time to start. So welcome again from my side. My name is Maxime Flamand, Chief Technology Officer for 5GA. We are here looking at this work item that is related to improving position and situational awareness through connected sensors. The work item was finalized some time ago, but we just published a couple of days ago the public technical report, which I invite you all to download. We're also going to post a link to the technical report on the chat. I guess that you will receive it to all. And I also would like to acknowledge the participation of all the 5G members to contribute to this quite extensive technical report, especially two persons or two organizations, especially so one who led the finalization is related to or that started the initial cooperation from Bosch on one side and represented here from with Andreas Schaller. And then the second that really put quite a lot of work in terms of technical aspects, and he will provide more technical highlight related to this work item. From Comsigna, András Váradi, thank you very much also again for your contributions. The work item had a short name, which was ConSens. We will, of course, tell you what ConSens means later. But in the meanwhile, I would like to invite anyone that wants to ask questions to post them on the Q&A function of the Teams tool, so that we can moderate this, and then I will be very glad to return these questions to the panelists here. So with no further ado, then I would like to pass on to Andreas Schaller from Robert Bosch, who will introduce the report. Thank you, Andreas.
Thank you very much, Maxime. So thank you everybody for joining this webinar and that you are interested in the results of the ConSens work item. So what is ConSens about? So as you all know, in the mobility area, positioning is a very important parameter. So we're always looking in improving positioning and getting accurate data of positioning. And it's an ongoing challenge to improve it and to also to reduce the cost, of course, of getting precise positioning data. There was a lot of challenges of different technologies in the past, and the idea of consent was actually not to invent a new positioning technology. It was about how we can create a system where different positioning mechanism can be combined. And this was the birth of the consent work item. So ConSens stands for Connected Sensors and Positioning as a Service, and it's about to get better levels of situation awareness and precise positioning. It's a service, so it other connectivity and other positioning techniques may be used, and that they will be fused, and there will be a synergy between the services to get to a better positioning for traffic participants. And traffic participants might not be vehicles only, it might be also VRUs. Because one of the challenges of the VRUs is that also of, let's say, low-cost vehicles is you cannot put so expensive equipment in these vehicle types as you can probably do in a AD level 4 autonomous vehicle. So the question is really, how can I get a better positioning for all traffic participants? So what did we look in? There were two different aspects we looked into. One might be already known. So of course you can use sensors in the environment to improve the positioning of any traffic participants on the road. You can build up this digital twin, and and in the road infrastructure there might be sensors, and based on that you can get better data about the positioning and the maneuvering of all the different traffic participants and increase the precision and trustworthiness of these traffic participants. So that's one thing. It's pretty much known. Many people do that. We see this especially for AD level 4 vehicles in the world where intersections are already digital twins of intersections are already used to improve AD level 4 vehicles perception. What we now looked into is a little bit more from a system perspective. What different system levels does exist? What is the data flow? What is the business model behind it? So you do not have to go into all these areas now. In the details, please have a look at the report to study it. It's really about that you have a positioning service and you have a service provider, and every vehicle can get this service. Or in the middle, there is a road operator offering this service to all the traffic participants and sharing the optimized positioning. And third, most right, there could be one third party offering this service for the complete ecosystem. That's the right picture. So there are different systems. All these different systems and are currently tested somehow in the world. And now in the report, you can see what are the difference and how precise positioning by fusing all this information can work. One concrete example we also looked in is something you may already know. Everybody is aware of UWB and everybody is aware of V2X. So we use ultra wideband in the vehicle, for example, for detecting child left behind. It's an NCAP use case, and you can detect human beings in the inside of the vehicle. So it's a well-known technology for detecting people, ranging, proximity, ranging. And we use this also very many OEMs for keyless entry in the vehicle. So it's also already rolled out globally in many vehicles that you can use ultra wideband to get a exact range between you and the vehicle. It's proven by the insurance company that your car will not be stolen and there will be no theft of your key in between listening to the communication. So it's a well-known safety and accurate technology for range detection. It's done by the Connected Car Consortium, and it's also defined by the FIRA Consortium, which is looking into ultra-wideband. One thing they are also looking in is now, you could also use the same technology if you do a drive-through, for example, to a fast food restaurant. So by driving through, you get the exact location, and with this exact location, you can do payment. And then it's not you have to reach out the mobile phone, and you cannot reach the other device, and it's very hard for you to use the service. No, you just have to drive through this payment area with the vehicle and you pay. So the next step actually is that people are looking into, can we use the same technology for parking? Can we do automated parking with ultra wideband in the vehicle, now looking outside, not inside? So we started with a child inside, now we are outside. We started with keyless entry with ultra wideband and Bluetooth. Now can we combine ultra wideband with V2X? Can we do the same thing again outside of the vehicle with two different wireless technologies? And of course, then you could improve the positioning related to the vehicle for VR use. Because the vehicle, which has ADAS system and high AD level 2++, have an exact position. So this is actually what was one of the ideas behind when we looked into ConSens. So how can we use both technology together and use it to get an exact position of a vehicle, of a traffic participant, of a motorcycle, of a bicycle, which do not have an exact position themselves. So that's the idea and the introduction a little bit to the project, to the work item. And now I would like to hand over to Andras for all the details.
Thank you, Andreas. Thank you, everyone, for joining. It's a pleasure. So after Andreas's highlights, allow me to go a little bit into my favorite part, the technical details. And let me start off by explaining you how we started the work and how we arrived at some of the conclusions, because this is a quite complex work item from a point of view that we really needed to harmonize very separate domains of connected automated driving and connected vehicles and CITS. So let me just start off by telling you some of the stories. One of the key problems that, thanks to, for example, the great work of Yunpeng and Ericsson, the whole ConSens framework is rather not limited to side link, but it's actually a solar technology, so service based on solar technology. So it works on various architectures that you could see from Andreas's slides. That means that we have several data links that are involved, and these data links and these technologies all have their own identity management. And we needed to figure out that if we are providing a service, how does the different actors in the service, or the two actors involved in a service exchange, identify themselves because we have so many. If you go along the example of Andreas on UVB has their own identity management. We have identity management on cooperative ITS with the station ID, but we have also identity management on classic 4G and 5G networks. So what to use in order to advertise the services and to establish links. The other very deep topic is positioning mismatch, and how do we help Fusion, because in the end what you're doing is improving a digital twin and improving your current Fusion of all the different detections. So there are usually more than one sources of information for example, a bicycle. And how do we deal with positioning mismatch? And let me also refer to the positioning and timing norm from ETSI, which describes how positioning should be detailed. This is actually the type of data that we would like to improve with the ConSens service. And positioning is not just 2 coordinates and that's it. Actually, 2 coordinates are the basic or the basis for the whole thing. But first of all, for all coordinates, we have confidence ellipses or confidence values, meaning that you never know. I mean, you're never right. There is no sensor measurement that is actually on the spot. There is always a detection error. So those errors, no matter what kind of message or technology we use, those errors should and are being put alongside the measurement result as well. We also have, it's not just positioning, it's also speed, heading, acceleration, for example. So there are actually, when we are fusing data, for example, between a radar detection and a vulnerable road user's own BSM or CAM, we are mixing not just the coordinates, but all these other details as well. And all of these details will differ, obviously, because you, again, never measure the same. So that entity's CAM and your radar's detection or sensor fusion, ego sensor fusion measurement will never be exact. So you need to fuse, and you need to be able to identify and deal with the mismatches. Then came the problem of prioritization. Every single medium and every single service has its own limitations. So how do we decide on what to include or how to prioritize between service requests, and which channels or which technologies to use, or how to decide between PC5 and UU-based services. Because it's also quite hard to detect which detection or which request is more important, because the safety rating, for example, from a safety rating point of view, you need to be able to identify, and you need to be able to communicate how severe is your request. So we needed to deal with prioritization and how to put an order between the service requests. Classification and content mismatch is, again, harmonizing the different types of data and classification to ensure consistency. Data does not necessarily need to arrive in the same form or format. So that's also a question if the sender and the transmitter is using different formats. And we will talk about different formats at the digital twin part soon. You also need to be able to translate between different types of content. Timing mismatch is also one of my favorites, because if you could imagine that time is constant, but actually also within traffic participants and also within a single traffic entity, a vehicle or a bike, the time is not constant. All the different ECUs, the different sensors, they all have their own timestamping. You are actually not allowed to timestamp at one single location unless you deal with the delta times, because all the sensor measurements needs to be timestamped as soon as possible, because otherwise you never know when the sensor measurement was made. That results in different times and different deltas between these clocks, within a vehicle. And that needs to be dealt with properly. And there is maximum limits on how high this can be. And then think about it, that every single vehicle's own clock and own version of time has also some sort of deltas, because again, in a non-ideal world, every single clock has some sort of delta. So how does this service tolerate time mismatch? And the third one was real-time data sharing and identifying the method for sharing the data, which is beyond the capacities of existing V2X systems, and how really we deal with the direct communication and this kind of sharing. Here, really talking about, for example, the use of CPM and SDSM, and the use of for example, other data forms like sensors. But I will talk about that in a sec. So the document also, the document starts with an overview of the existing localization technologies, and you need to be aware that that the physics and the algorithms are pretty standard. So the basics of localization and positioning is rather stable, which means that actually all of the listed technologies are more or less using the same methods or the same basics for localization. That means that two-way ranging or angle of arrival is the method of detection is found in many of these examples. But it's also very important to note that each has their own properties and each differ from the other, and that was also one of the very interesting things. So how do we use the best out of all the worlds? Because if you think about, for example, 5G network-based positioning, it also offers, for example, round-trip time or time of arrival or angle of arrival-based positioning. But this service is always based on the towers and the user equipment down there. So the positioning system or setup is between the cells and the user equipment. While if you go into 5G side link positioning, again, the methods are the same, but obviously the user equipments themselves start positioning themselves among each other. So for example, if you're talking about relative positioning, it will not be anymore about how far are you from the cell tower or what is your location compared to the cell tower, but between two user equipments, which is actually what we focused on more in this use case for the vulnerable road user and the vehicle. When it comes to ultra-wideband positioning, let me add that UVB has a quite a big spectrum. So from a spectrum point of view, that's a very nice asset that they have, and it makes UVB a very robust technology and can be very precise. But by the way, the range is, for example, much smaller than 5G sidelink, and obviously sidelink is also different from the 5G network-based positioning. And let me also add that the sidelink positioning was actually introduced in release 18, and does have some advanced technologies like proximity service. And also let me add that the EPOS work item from 5GAA has already gone into some of the details on this positioning technology. Finally, arriving to the GNSS based positioning, you all know this, but maybe you don't know that actually the European Space Agency and the Galileo team and the LEO PNT team is working on obviously working on new services. So apart from precise point positioning, so PVP and RTK, which is there for a long time, we have also now the satellite-based augmentation service called SBAS, and we also have differential GNSS. And lately, we have been introduced the Galileo high accuracy service, which are new precise positioning services available in Europe, and which are very well augmenting the existing positioning services that we have taken a look at here. And again, what you need to see is that these positioning services all help the ego vehicle or the traffic participants to position themselves, but they have very, very different characteristics, and every single vehicle will implement these positioning solutions in a different way. Andreas mentioned that not everything is achievable or available for low-end vehicle or mass vehicles, which have a very strict price point. You cannot have every single technology in there because of the price limitations. So you need to leverage what you can achieve with commercially available automotive solutions if you're a vehicle manufacturer, for example. So it's always a give and take from that point of view. So coming down to the ConSens service, how does it look like? I'm going to use the example what again Andreas was saying. For one of the first use cases introduced by Bosch at the beginning of the work item was what happens if we have a vehicle and a bicycle in an urban environment, and what happens if their basic awareness of each other is just not available. So let's say that we have a car and a bicycle. Let's say we have some radar detections, but maybe it's a lot of vehicles. Maybe there are obscurants, so it's not perfect. And what if we have a basic BSM or VAM service coming from the bike, but the detection is not precise enough for the particular ODD or the particular safety application that we want to have. And what happens if, for example, that bike is featured with some sort of UVB service, the car has, for example, been equipped with keyless entry, and what if we would take those UVBs and would do something with it? So how it works is that you first you're there with your basic awareness of the environment. It can come again from radar detection, it can come from BSM scans. Somehow you know that the two of you are in or might be in a collision course. So once this is done, you do a situation assessment, and that situation assessment results in you not being enough sure or not having the confidence or the precision to make a decision of alerting or avoiding for that bicycle or not. What you can do here with the ConSens service is identify this actor. Again, with the situation assessment, you know that there's a bike and you're identified that bike. You communicate out that you need to improve your situation assessment. You need more precise localization between the two actors. And this, in this particular example, triggers a UVB or PC5-based relative localization triangulation method or angle of arrival, whatever the chosen. So it can still be, different algorithms can be implemented or different ways can be implemented based on what services or what sub-services the two actors are implementing. So that means that a session, either a PC5 session or a UVB session is initiated, and the exchange starts and the triangulation starts, or the angle of arrival measurement or time of flight measurement starts, improving the detection over at both sides, obviously, but let's look at the vehicle side. So the vehicle side, for example, started off with 2 meters of precision. So we didn't even know which lane that bicycle could be in, but ended up after the triangulation with maybe 10 centimeters of precision. So it knows now much better where the bike is, and then can make a decision if it wants to, alert the driver or do soft braking or whatever that particular ODD and the implementation allows us. And that is currently how this service is. So first, there is a situation assessment, identifying that there is a situation. I need to improve the data in the situation because I can't make proper judgment. I make a request that is being responded, we improve both our data, and we reassess the situation, hopefully in a better environment. So in a nutshell, that's one of the main core ideas behind ConSens, and how the 5G network can be used for these two actors to find each other. And then let's talk a little bit about the digital twins, what the digital twins are for, how they work, and why they are important. So first of all, digital twins allow this situation assessment to happen. Second, the result of the ConSens service is an improvement of the local implementation or the local database of the digital twin. The digital twin is actually, in case you're not familiar, it's a concept. It can be called sometimes the local dynamic map. So Etsy had, for example, that terminology being used. And there is actually right now quite heavy standardization of the digital twin in ISO. But coming back, the digital twin is actually a multi-layered database, with each layer being updated by different services. And this layered digital twin obviously starts from some sort of map, which changes only once a month or once a week, can be provided by all the different map providers. And then, as you know from the map providers, there are more dynamic layers when you go up on the layers. So there are road constructions. There might be events, long-term events on another layer on top of the layer, and also something. So an SD, a lane level map, can have actually an HD map on top of it, having much more precision, maybe lane information, maybe even centimeter precise information about objects and lanes and other parameters of the road. And once you go up to this point, and let me mention that, for example, different standards are being used to update different types of the layer, and there is overlap. So there are some objects, for example, that Sensoris support, and Sensoris is a cloud-based service. And then there are CPM, so sensor detection sharing message and collective perception sharing message, which is the sidelink equivalent, or the sidelink technology from Etsy and SAE, which allows you to again share objects. But and when you come to really low latency and time critical objects, you usually use obviously sidelink. But what I wanted to mention is that at the end of the traffic jam or a stationary vehicle can actually arrive to your digital twin in the vehicle, for example, if you're a vehicle, from different means. And you need to deal with that on different layers and harmonize that. The other aspect, what is important to mention is that the update rate or the technology used also depends on how dynamic that object is, because, for example, a running moose or a deer that is crossing your road, that's also something you want to put in your perception, your digital twin, on the very top layer, the very most dynamic layer. And that's not something you really want to, send up to the cloud and store for hours, because that information is out of date in 2 seconds, because the running moose is that the location of the running moose is obviously changing in every second. And you can argue that maybe animal on the road is something for longer term, but for example, which lane that moose is actually just valid for a few seconds. Very important point is that every single digital twin implementation is different. So every single vehicle's digital twin is different because their feed, so the information it's fed is different. First of all, vehicles differentiate between what kind of services is available, where they had bandwidth, where they didn't have bandwidth, and all the detections are different because they are just built differently. So this causes every single instance to be something different. Actually, also important to note that we need to care for error propagation, because if you start putting an error into your digital twin and you're sharing this digital twin, for example, by the use of CPM, if there is a mistake in there and you share it with the others, then the others will also have that mistake. And if they retransmit errors data, then actually false measurements and false information can arrive. So actually exchanging of digital twins must be made in a way that you make sure that there is no third-party measurement in them, because otherwise, again, error propagation can happen and phantoms can appear. But let's maybe not go so deep into the technical details. Precision is also varying, so that means that your digital twin, as we mentioned, have different precisions for every object and every detection. Not just precision varies, but also trust and cybersecurity. So you might have a secure link to a perception service, or you might have a secure link to GNSS, for example, via OSMNA. That information will be on a different trust level in your digital twin than something else. So you might want to update something not just based on lack of precision, but on lack of cybersecurity and lack of trust. In any way, the situation assessments are always happening on this digital twin. That means that all vehicle functions, for example, forward collision warning or intersection movement assist, or these run on the top of this perception layer and this digital twin. And this is the digital twin is used to identify the different actors which trigger a ConSens. So you go and you can use the forward collision warning example for the bicycle, or another bicycle could be from one of our previous projects called ProPart, where we wanted to do an automated lane change with a truck. And if you don't have enough high confidence information about the lane beside you, you cannot move into that lane. So in that case, you can actually use the ConSens service to ask other stations and neighbors to improve your perception for that particular area. The exchange of ConSens can actually support multiple types of digital twin exchange. The UVB was a one-to-one, so actually I'm improving the relative measurement of the vehicle. So actually I will only improve one single entity, the bicycle, in my digital twin. Or you can actually also use CPM or SDSM, which is the sensor sharing or perception sharing. That actually improves, if you get a new CPM, that improves a lot of different actors into your LDM, and you can basically send over groups. Before I run out of time, let me mention that digital twins use different might use different coordinate systems. We use in Europe and at CITS VGS84 as the coordinate system, but every single vehicle also has, or most of the vehicles have relative coordinate systems or mathematical representation of objects. For example, with the use of occupancy matrices and other methods, and those are not aligned with each other. So you cannot actually take your occupancy matrix and just share it with the others, because the coordinate system will never work. So that's also something to keep in mind when you're sharing information. And actually UVB localization or SDSM and CPM solve this problem by translating them into either a relative coordinate system without the requirement for a coordinate system, or VGS84, which is the standard coordinate system. Privacy aspects, obviously for digital twins, it's the way we solve it right now is either you use anonymized data, which cannot be traced back, or we use temporary data. Actually, the digital twins, especially the higher dynamic layers, are something that you only store temporarily because the information is out of date. quite fast. And with that, let me also go to the next slide and say that actually this. So we covered most of the topics with Andreas. However, there are a lot of additional topics like business aspects or go-to-market strategies, future work, what needs to be done, and a lot of other things in the work item. So please do take the time and read it. It's quite a material. Thank you so much. Over to you, Maxim.
Thank you very much, Andras. And Andreas, I invite you to take the floor so we can have some questions. I posted some questions myself, which we had more or less prepared before. So, but I also invite anyone that is in the audience to post their questions so that we can also answer questions from the audience, from anyone that is curious. I have a first questions related to the actual implementations of these concepts and to what extent these have been put together into proof of concept, or whether this has been tested in projects, or even whether this is even being deployed somewhere in the world. Can you just give some indications on where we are in terms of evolution? And
I mean, yeah, maybe from the infrastructure point of view, you may all know that there's a lot of money in China flowing into infrastructure. And yes, there are some implementation in using sensor sharing messages for AD level 4 vehicles in China, and there were POCs in the Shanghai area. So yes, there is something going on for the ultra wideband. It's an idea. It was an idea we looked into. So far, it's not implemented into a POC.
thanks, Andreas. Andras, do you want to comment as well?
Yeah, I mean, we actually wanted to do a demonstration for one of the 5GAA weeks. That hasn't happened yet, but we are quite open to do something like this. Again, some implementations or some concepts were taken for real. So the system is being implemented in some parts, but the whole concept and this service, as we defined, is not yet done. So we are quite open, and that's one of the future aspects.
Thanks, Andreas and Natasha. So you mentioned China. Can we? Are the concepts similar, or how do you see China compared to other places? This is another question that I posted.
I mean, Andras and Maxim, maybe I start. So in this UNECE web session, there was VRU one of the topic, and we saw that China had come up with 3 options, technology options to be deployed and to be looked into in China. One was the infrastructure, but there was also enabled VRUs was one of the options. So the answer is yes, they are looking into these 2 scenarios also, and they do talks, and they try to understand how to include VRUs into their vehicle road cloud infrastructure system.
Thanks, and maybe just a thought from myself. So to be honest, I don't know if they exactly have the similar approach, because I also are aware of the VRU safety use cases and that they are using sensor perception. But where ConSens goes beyond is the request, so that you are not just allowing a passive service of, I don't know, for example, SDSM sensor sharing, but an ODD, so a vehicle's own system, can say that, hey, the current services which are there for, that are operating, is not enough for me. So please temporarily improve your service, temporarily allow me higher bandwidth or more services or a more precise service, and let's do a UVB session. So that proactivity that can be triggered from a situation assessment was something quite new that was brought in via the ConSens work item.
Great, thank you. I posted also a few questions, and at the same time, I'm looking at questions from the audience. Questions related to the accuracy of the solutions, and especially when you combine different sources. You mentioned, Andras, the error propagation danger. And so, of course, you can have a super nice positioning system, and then someone else tells you something completely different. And so, you need to be able in the system to detect erroneous inputs. Was there in your assessment among GNSS 5G positioning from sidelink point of view, ultra wideband sensor fusion, was there some combinations that really made a difference or that you would recommend? Thanks.
Yeah, so technically, I mean, the default use case of combining UU or PC5 for the session establishment and then UVB was something quite nice, because UVB shines when we are around 10 meters. Our technology, so I mean, the range of UU. You know that PC5 starts working approximately at 4 digits, so around 1,000 meters or 1,000 something, and so the ranges are higher, but we also have a much smaller spectrum. So if you are quite close, and obviously frontal collisions or intersection collisions happen when we are quite close to each other, UVB works within this 10 meter, 20 meter range. And since it has, in most places of the world, a very high or very wide spectrum, it can be quite accurate. So that's a winning combination of exchange. And regarding error propagation and trust, so that is why I really like that Andreas mentioned the FIRA consortium. So it depends on what kind of framework we are under. So FIRA also provides some ranging capabilities, and based on those specifications, either they deal or doesn't deal with how error is treated and what kind of compliance metrics are there. So it depends on what technology or what technology sub-choice is being used and what framework this exchange is under. And I think that, by the way, and that's also some parts of the future work, that we don't have a completely harmonized trust ecosystem within, for example, mixing UVB localization with PC5 localization.
Good. Andreas, you want to complement or no?
There's not so much to
follow up. I can perhaps follow up on asking, so in numbers, did you study what kind of improvements you could make in terms of, for example, but absolute or relative positioning, but even in terms of latency? Didn't you observe also challenges in the latency of your positioning?
I mean, it depends now what technology you use, but I mean, where are we coming from? I mean, if we under open sky condition, then you have a good GPS in a mobile phone, and it would be perfect for a VRU. In an urban canyon, you might not get these, or you will not get these, and that's the point. And then you say, okay, if I now need, because I'm in the urban canyon, I now need an improvement of the accuracy. Then I could use the concept of ConSens. I think that's where we were coming from. And I mean, it's 10, 20 meters. So if I know if there is a bicycle, if dooring is happening, I would like to know where is this bicycle. And if I'm now 5, 6 meters off in an urban canyon, I don't know where this bicycle is. Is it on the bike lane? Is it on the street? Is it left or right? I don't know. And that's the point. I mean, if I really would like to be precise on a lane in an urban canyon, I have to find a cheap solution, which I can get easily on a bike fleet, for example. And I cannot make a expensive investment in the bikes too, or in the motorcycles. I cannot put 80 level accuracy and ECUs in a motorcycle. It will not be possible. So I have to come up with an idea. And the point is really, of course, in an urban, you can always do certain intersections, but you cannot do all street. And that's where we also were looking for, is there any solution? What could be a solution? That were all so initial ideas coming out, where the project was starting. And people ask, is there already a solution there? No, there is not a complete solution there. It's still open. Maybe people would like to PhD project, and people would like to look more closer on it. And yeah, I think this is still an open question.
Yeah, and let me add that actually the beauty or the one of the core ideas is to transfer from absolute coordinate system to a relative measurement. Because going with Andreas's example, if you have two entities, a bicycle and the car, and they have, I don't know, 1.5 meters of precision from a very precise GNSS solution in an urban canyon, 1.5 meters of confidence for each, that if you add that together, it's 3 meters of delta. So you can actually have 3 meters of error in there, which is not enough. I mean, that's again not even or not even lane level. And because you need to translate it to absolute coordinates and then pass it over, so he can have an error, I can have an error, and we need to add those errors together. But once you go in this environment, once you go to relative, that doesn't have this kind of problem. So if we start with a UVB session or PC5 side link session, you get rid of this absolute conversation error, and you get the results were actually around the decimeter level for the initial tests. And that's quite nice, because for decimeter level, that's almost enough for ADAS use cases.
Thank you. I have a question here in terms of the liabilities and the willingness to engage in responsibilities to provide these kind of services. So, for example, a public road operator that would provide this infrastructure-based position service. So, what would be the possible solutions to circumvent the challenge with regards to the legal model or the business model of providing this service without all the liability that comes with it?
From my point of view, I would put it put it under the CITS liability framework. Sorry, Andreas, go ahead.
No, I mean, if we speak about the infrastructure story, then I mean, there was now this nice paper by 6G joint undertaking SNS about the infrastructure for rail and road in Europe for the corridors. And I mean, the networks are now a part of the infrastructure, which has to be safe and secure, and resilient. And so as soon as we get, let's say, resilient networks for rail infrastructure, we might also use it for a road. And then in that case, if you really get what is the plan to roll out infrastructure, let's say, roll out infrastructure for rail, for high-speed rail and highways, which are mostly in parallel. And then you provide these services for rail and road, you get services from network operators in positioning and in timing for both transportation methods. And then you, of course, have this third-party kind of engagement, because then you have a synergy between different transportation modes, requesting timing and positioning. That may be a way to roll it out across corridors. It's now not cities, so for cities, I think it's still interesting how to do it. Not clear. I mean, in China, it's clear there is a metropolitan regions, and they will just have one of the MNOs responsible for all the metropolitan regions in China. They will do it. It's one MNO, and he will just be the one. In Europe, it's not so easy.
And Andreas?
No, I think Andreas said it all.
So you're, but do you foresee that that cities would start to install these services, or this is provided by private entities? That's what I understood from Andreas. Andreas.
Yeah, I mean, I think cities are very interested in investing into anything that can help VRUs and their communities. And again, I mean, and ConSens is unique because it is quite resource saving. That means that you cannot serve everyone all the time with very high, because you will run out of medium. And what ConSens allows is it allows vehicles and traffic participants to request for a short period of time additional resources, and therefore it's from a business point of view, it's actually better than the basic concept of CPM. Of course, both is very important, but it extends sensor sharing and other VRU safety methods already being deployed on streets. So I believe it's a good additional investment. It has good potential.
Well, we come almost at the end of this webinar. I would like to thank you very much, Andreas and Andreas. This was a very good overview of this technical report. I would like to remind that there is the technical report is available for download with this QR code, but that as well there is a posted a link, so don't hesitate to just go and look at this. Again, thank you very much, and thanks to the audience for bearing with us for this conversation. Bye-bye.
Thank you. Bye.
Thank you, everyone. Bye. Thank you for your time.